Today we are going to start a new chapter. So in the work, energy, and power, what is most fundamental of all three? What is most fundamental? In the work, energy, and power, what you think or believe is most fundamental? Is it work, is it energy, or is it power?
So energy.
Energy. So what is energy? What is energy?
So ability to do work.
Very good. So it is the capacity to doing work. Okay. So how much work an individual and agent can perform depends on how much energy you have already. So you cannot work beyond what you have. So for example, we as a human, we do work because we have stored enormous amount of energy. So in human body, we have cell and there we have mitochondria, which is called the powerhouse. So energy is stored and that energy we consume to walk, to stretch the muscles, to jump, to run, to even to speak. So these are the muscular work in which the muscles are either getting pulled or pushed or stretched, compressed. So every human activity leads to some internal work, and these work gets the energy from the energy stored. And we feel tired when the energy stored gets consumed. So in order to replenish, we need to sleep for a good amount of time. And the body will be able to regenerate or store the energy through the metabolic reaction. And to generate energy through the metabolic reaction, we need to eat some food. So food is a complex nitrogenous compounds also, or maybe some other compounds, maybe some organic compounds, complex organic molecules. And these complex organic molecules, what we call food, when you eat, then the different, you can say, uh, hormones, juices, acids, and so many other things, they react, they break down these complex molecules into simpler molecules. They break into small pieces. And the breaking of bond releases the energy. It's a chemical reaction basically. And these bond energy which is released is actually getting stored. And apart from this energy, we also store some other byproduct like fat and other things also, which body uses for the other, requirement or situation. If it is not getting consumed, it gets accumulated over the time, and then we have the fat, okay, as you know. So energy is a concept, and human beings are able to generate through the very complex process of consuming food, and the food consumption is eventually the complex, you can say, organic compounds, and eventually the using some catalyst, they react. So we do have the juices in the stomach, some acid we have, which help in digestion. Okay, so in when it passes through the intestine, it releases some sort of liquid, some chemical, which helps you in digestion. So eventually, a lot of chemical reaction undergoes within the body itself, and that is how we produce it. So we have the internal mechanism of producing the energy. Okay. In case of car, they don't have that ability like us, but they do have a mechanism of producing energy. So you add a diesel or petrol. Okay. And these are carbon compounds. And upon ignition, these compounds, or you can say these liquids, what we call fuel, will burn. And the burning is actually oxidation process in which again you release a lot of energy. And with this energy, we have of course something called the thermodynamic engine. So in which we have a gas filled. So these energy is absorbed by the gas, which expands, and then there is a piston attached to this cylinder. The piston is pressed by the gas, which in turn presses the crankshaft, which in turn turns the wheel or the gear system. And that is how the energy requirement is fulfilled. So of course, we need some way to derive energy. And of course, you cannot, run your bike or a car beyond the energy availability. So if you have energy which is available in terms of fuel, so once fuel is completely consumed, you can't drive your car because there is no way to derive energy. What is very counterintuitive in our learning of work energy power, that the energy requirement is a different entity, but uh, the motion is not governed by the energy. The motion is, of course, required. We need some force to have acceleration, and that with that acceleration we can change the velocity. So Newton's laws of motion will help you in understanding the motion part. But to fulfill the energy requirement, we need to look for the source of energy. And sometimes it is very counterintuitive that every force which is acted upon on any object is not able to give energy. So not every force will give you energy. That's very interesting. So when you run or walk, then you walk with the help of which force? We have discussed this. Which force enable us to run or walk? Tell me.
Friction.
And which friction is it? Static or kinetic?
Static.
Okay. Now you will come to know the static friction which enable the motion. The same force do not give any energy. So the friction will never give you energy to walk or run. So the question is, when we are running, of course, the friction is enabling it, but the running is a process of stretching the muscle and compressing the muscle. Okay. And therefore, there is the energy consumption is within the body itself. Okay. So our energy requirement is not fulfilled by the friction. Of course, friction will support my motion. It doesn't mean the friction will also fulfill my energy requirements or energy needs. So our energy needs are fulfilled by the body internal energy production mechanism. The food which we eat, the metabolic reaction, and we say that people with a good metabolic rate can digest food easily. So metabolism is like a way to say that how quickly you can break down the complex organic compounds into simpler compounds. Do you have the required chemical available and can do this process faster? With age, this process will slow down. We do not have that similar ability to digest or eat. So, of course, as we grow, we can eat because of the habit, but we cannot digest because of the ability. So that's why, mostly when people grow old and if they're not doing a lot of exercise, they also become fat. So this is a very common process. Like when you eat in your younger days, you consume it completely because of your activity. You run, you walk, you play. And also at that age, your metabolism is very high. So whatever you eat, you are able to digest. But as you grow old, things will change. And therefore you have to work actually extra more than required to digest that extra energy which you're producing. And if you're not doing so, then it will accumulate, which is also not good. Okay. So energy is the basis, and it is produced by a different mechanism. Motion is something different, and we need to understand that motion and energy are not always directly related. So it means every force which enable the motion is not the force which give the energy. Okay. So it happens many a times. Okay. And what we are going to learn in this chapter is that how energy, kind of get exchanged in the due process of interaction of one body with another body. When a body interact with the force, sometimes the force will be visible to you, sometimes it will be invisible to you, but you need to understand that how force interact in a way to exchange energy. Okay, so we are going to learn that energy is something like a storage. It's like a bucket of water which you have, and work is like, taking the mug and, taking the one mug of water and giving to other, or maybe you can take water from other and pour to your bucket. So work is a method by which you exchange what you have, or you take from other what they have. But you cannot, do the work if there is no water in the bucket. Okay, so you cannot move your mug and give someone else water if you don't have the water in your own bucket. Okay, so let's say the Holi just happened, and if you want to throw the water balloon, you should have the water balloon. That's it. Then only can throw it. Okay, so if you have only balloon, will you throw the water balloon? No, because you should have the water before you can throw it. So the balloon must be filled with water. So similarly, energy is like every person, every agent in the world, they have got some invisible bucket which is storing the energy. And work is a method or mean by which these energy, the stored energies are exchanged. Okay. So when someone will ask you, what is work? What will define? Is work energy, or is work a way to exchange energy?
Way to exchange.
So work will never tell you how much water is in your bucket, but work will tell you how much energy you gave to other or you received from other. So work can only tell you the transferable part, right? Not the absolute part. Do you realize this, what I'm saying?
Yes.
What work gives you the idea? The amount which got transferred, not the amount which you have, isn't it? So if you give me 10 rupees, can I guess that you have only 10 rupees in your life? Or you may have more, you may have much more than 10. So can I guess how much you have if you give me 10?
No, sir.
So what I can say about this 10? That you must have at least 10. Correct?
Yes, sir.
If you have given me 10 rupees, then I can say the least amount that you must have is 10. But you can have any amount more than 10 or equals to 10, right? So
Yes.
work is like, you take one mug or one glass of water from your reservoir and you give it to other, or you may take someone else's water and add to your reservoir. The work is that method. It's a mode of energy exchange. And why we call this name the work? Because energy exchange can be done in various ways, need not to be just physical way. So we do have something called the heat exchange process, in which when you touch a high temperature body with a low temperature body, the energy goes from high temperature to low temperature. And here we do not need something like a mug, we do not need something like a force or displacement. So this is also a way in which energy is exchanged, but because of this very different nature of energy exchange, okay, the name given to this process, we put a different name. Actually, we call it the heat. So heat is again a method of energy exchange. Work is again a method of energy exchange, and they are given different names because their process are different. So when energy is exchanged by virtue of temperature difference, then that energy exchange we call, what we call?
No.
Heat. When the energy is exchanged by virtue of difference of temperature, then what we call?
Heat.
You don't go and give, no? It happens due to conduction, convection, radiation. So let's say if you touch an iron rod, what will happen? Energy will come to you. Assume the iron rod is hot. So if you touch any hot body, will you receive energy? Yes or no?
Yes.
Is the rod giving energy by taking energy in a bucket or in a mug or a glass and giving to you, or it is happening because of the direct contact itself?
Because of the contact.
Is there any physical movement required?
No.
No. So because here energy is given without the movement. Okay. Understood what I'm saying? So the nature, in nature, we have energy, reservoirs, a large energy reservoirs everywhere. And you want to take that energy. And to take that energy, you have to perform some act. And these act can be called work. Sometimes these act can be called heat. Okay. So the whole idea of this chapter is to understand that we are actually going to talk about one of the act actually, one of the method actually in which energy can be exchanged. Our intention is not to understand every form of energy. Right now, our only intention is to understand one particular way of energy exchange, and this one particular way is called work. And in this particular process, two things are required. The one is called the force, the involvement of force, and the other part is called the displacement of point of application of force. Okay, so here we see some physical movement, and when the point of application of force is moving under the application of force, of course, then we say some sort of work is being done and some sort of energy is being given or taken away. And to understand the direction of energy flow, we have some sign convention. So when you say that a force has done positive work on you, a positive work by the force means you are the recipient of energy, and the person who applied that force was the giver, the center of the energy. Okay. So you extracted energy from that guy and you added to your own kitty, your own bucket. Okay. So energy is, of course, the capacity of doing work, because you can give to someone or take away from someone if they have the pre-stored energy. Without energy stored, you can't talk about it. Understand what I'm saying?
Yes.
Okay. Sometimes the same energy concept, what we are calling work, we sometimes we don't like the work definition, and we create something very interesting way to tell you the same thing, and we term as potential energy. So let's say potential energy is an alternative to tell you the work actually. I mean, it is like I don't know how much water is in a bucket. Okay. But you give me, let's say, one mug of water to me. Okay. Now, if I don't know your energy and if I name it as zero, if you give me, let's say, one bucket, one mug, then can I say your energy will decrease by one? Correct. So the initial energy, if I name it as zero, then what is the new energy available to you? We can say the new energy is negative, right? So we say you have minus one bucket of energy. And this way of writing we call potential. So again, potential is nothing new actually, and there's nothing like a potential. It's like it is always work being expressed in a different terminology. So always remember that there is nothing like potential energy per se. We have defined this unique term for the purpose of convenience. Okay, so it is just a matter of writing. It's a matter of discussion, and because of that discussion, we define it. So when we learn this concept of potential energy, we'll go in detail about it, like why this was defined and how it is so useful, and how it can eliminate the need to write work in many cases. So in some cases, work is easy to write, but in some cases, potential is easy to write. So we see that which way is easier, and once we realize that which way is easier, we choose that way to solve the numerical. So always remember that work and energy can be exchanged in variety of situation. And when we talk about work, we never talk about the potential. So it means if we want to talk about potential, we should not talk about the work. Okay. So for example, if someone is willing to talk about the gravitational potential energy in a given column or situation. So if you want to talk about the gravitational potential energy, it means you should not talk about which energy, which work. If you want to talk about the gravitational potential energy, then which work should not be taken into consideration? The answer is work done by gravity itself. Because writing the gravitational potential and also writing the work done by gravity is like doing the same process twice. So that will always create an error. Okay. So one can only stick to one method. So either you understand work, then you're not supposed to understand energy at all. I mean, the potential is not at all useful. I mean, not required. I mean, I won't say it's useful. It's like it's not necessary. I mean, if you understand work really well, you can do any question in physics. But sometimes we have seen that writing potential is way too convenient than writing the work again and again. And the reason is because of the simplicity of its formula, because of its scalar property. So work requires taking the dot of two vectors. If you remember the definition of work, the force dot displacement, right? If you have heard this in class, I mean, it was in the chapter of vector. Do you remember the work definition?
Yes, sir.
So you can also realize that writing force and displacement dot product may be cumbersome, and you also need to integrate, which is even more difficult task. So potential is the final result. So what we do is the integration will give you some answer which we can treat as a formula, and we can directly apply the formula, and we need not to bother about the entire integration part. So as you go in the chapter of gravitation, electrostatics, magnetism in class 12 syllabus, in all these three chapters, you will see that sorry, more very often we do not use work, rather we use potential energy to write things because that has been really convenient so far. So this chapter is the basis for the entire 12th chapter, which you come across very soon. And there you will see that the same ideas we are going to use. So take this chapter again as seriously as possible, because this is going to be the fourth fundamental chapter of physics. And understanding of energy is very crucial to move forward in mechanics. Now the question is, why we need to study this chapter? What is the motivation behind this chapter? And because force is something which we have studied in laws of motion, we know how to write force. And when it comes to displacement, then we can always write F dot ds. We can integrate also. So if work is defined in terms of force and displacement, uh, the idea is if we can understand force, we can also understand the motion. And we have seen that using force, you can find acceleration, using acceleration, you can find the velocity, and you can do so many things. Then why suddenly we need to study this chapter? If force give you the motion, then why energy? Because eventually energy will also give you motion, right? So why we need to study this chapter? Any guess? Okay, I'm just asking guess. How this chapter is going to, add something meaningful to your life? Just a guess. No idea. Hello, hello. Okay. The answer is to write the laws of motion. If you remember, what you need is you need a FBD, right? Free body diagram. And what else you need? You need to know the direction of motion, isn't it?
Yes.
So you need to know the path actually. I mean, a well-defined path will have well-defined laws of motion, and then we can solve. But you will come across a variety of situations in which the path can be very complex. Let's say if you want to go from a mountain range to another mountain range, and this path is not at all curvilinear. I mean, it's not even proper curvilinear. It's not even rectilinear. It is having some peaks, valleys. So writing the laws of motion, let's say if you want to write a mg sin theta minus mu s n cos theta, mu s cos theta mg cos theta equals to mass into acceleration. What will happen is as you go, the theta will change, right?
Yes.
So is it possible to integrate things on this random path? The answer is very, very difficult. So even for a simplest situation, let's say if it is entirely smooth track, there is no friction at all. The thing is, if you want to define the motion, you want to relate V1 and V2 for this random path, it is going to be extremely tricky or very difficult. But the beauty of energy is that sometimes, I mean, when the things are very nice, it's called the conservative force, will come across later on. So under the conservative force, the relationship is independent of path. So no matter which path you choose to go there, having the information of your initial and the final location is sufficient to solve the question. And that is why we believe that energy is a really powerful method, and not just powerful, it is a method which can eliminate the need of knowing the path. Okay. But laws of motion is not the same. To write the laws of motion at every instant, you need to know the path at every instant. That's why the laws of motion becomes sometimes really cumbersome, or sometimes in fact it becomes impossible to solve. So laws of motion is of course the primary. Okay. Energy is like the most powerful tool. So you can say that what laws of motion can do can be done by energy method also. But vice versa is not true. So it is like a energy method is like a big set, and the laws of motion is a subset actually. So whatever you can do by laws of motion, the same thing you can do by energy method also, but not the vice versa. That's why energy is a bigger perspective of solving numerical. Okay. Let me remove all these things is not required. So we'll talk about work quickly. What is work? What is work?
Exchange of energy.
Yeah, it's a way, it's a method, it's a way by which energy can be exchanged between two bodies, system and surrounding. So that's the right definition. Let's just put in more mature wording. So we can say, please, a way in which energy can be exchanged between so this is the work. So in okay, what are the other ways of energy exchange that you are aware of? So other ways of energy exchange is
Heat.
heat. Okay. And what is the fundamental behavior of heat?
To travel from a body at higher temperature to a lower temperature.
Yeah. So it is means like the difference of temperature is the cause behind the energy exchange, right? Can we see
Yes.
energy?
No.
Is energy having any color, smell, taste?
No, sir.
So energy is simply energy, right? So when you name the energy by different word, it doesn't matter. Energy is simply energy. And no one knows what energy is. It's just like idea. So work is, this is the definition of work. People get confused between work and work done by the force. So work is this much, but work done by the force, actually people take the work done by the force definition as work. That's why they are confused. Work is not this. That's why I put this thing distinctly. Work done by the force is quite different, and work is the idea which we have discussed. So work done by the force is a definition, a mathematical definition. Okay. That how we say that a work is being done by the given force. So in the definition of work, in the method of energy exchange using the process called work, two things are required: force and displacement. So we say also say that it involves, or in this process, force and the displacement must be present. Which means like this process is only feasible if you come across some force and displacement. So what kind of displacement we talk about? We need to understand the idea of displacement. Okay. And from there we define the work done by the force. We write as WF. So what is the meaning of work done by the force? So there is a definition that you have to remember very carefully. So that's the definition. The definition we are going to write is only for the constant force. The definition of work done by constant force. So we do have a definition, but only for constant force. We don't have a definition as of now for a variable force. And we'll come to that, what is how to do the question of variable force if there is no definition. So what is the definition of work done? You know from vector chapter, what is the definition? It is defined as?
Force into displacement.
No, that is the biggest issue. It is defined as the product of force So try to read this sentence twice or thrice, and then I'll come back to this definition again. So you read the definition? And what is written? Point of application of force. Do you understand what is the meaning of this?
So
Point of
where force
application.
is applied.
Yeah, see, when we have a body can have a shape, it may have a dimension. So of course, in this chapter, what we study is called particle dynamics, in which we do not consider the dimension. But when you go further in the chapter of rotational dynamics, there the definition will actually help. So displacement of body is not considered. The motion of body is not at all meaningful to us. What is really meaningful is the displacement of point of application. Understood what I'm saying? Now,
Yes.
to understand this better, I'll give you. So you might have seen a ceiling fan. Have you seen ceiling fan? Do you have at home? You know ceiling fan? Ceiling fan.
Yes, sir.
In the ceiling fan, we have wings actually, right? So this is your ceiling fan, okay? Now, imagine someone is applying a force near the tip of the wing. And as a result, the wing will make some sort of movement. I'm keeping it very small for a purpose. I'll call this as DS. This is F. As a result of the motion of this wing, do you think that the center of fan has moved? Tell me.
No, sir.
So generally, when we say body, we look for the center of mass. And if you look at the center of mass, you can clearly see that even though I have applied force, there is some sort of displacement of point of application. But the fan as a whole, which is called the center of mass of fan, is not at all moving. And if fan is not moving, but that is not our concern, what is the definition of work? It is defined as the force into point of application. This is the point of application. And as a result of the movement, can you see the point of application has gone from here to here? Let's say the wing span is of length L from center. Tell me what is the displacement of point of application?
L into d theta.
Very good. You can clearly see this is L d theta. And it has happened in the direction of force, right? The direction of the displacement is in the direction of lines of force, yes or no? Tell me.
Yes, sir.
And therefore, okay, imagine at the same time, someone is also applying force like this along the wing. Let's call this F. And the displacement is same. The wing has gone from there to there. And because of the small displacement, we define elementary or small work, we call dW. And because we have two forces, so we have to define work done by each force separately. Try to apply the definition which we wrote on the left, the previous page, and tell me what we should write. The dWF1 is how much? It is the product of what?
Force
Force
and
and
displacement.
displacement of what? Force and displacement of correct.
Sort of point of application.
Do you realize what I am saying here? If you cannot remember this definition, you cannot solve any question of the chapter. So it is mandatory for all of you to remember the definition first. If you're okay with the definition, then we can move ahead. Are you okay?
Yes, sir.
So what should I write here? DW for the small work or elementary work by F1 is how much?
F1 into LD3.
What about the DWF2?
So 0.
Very good. Do you realize the purpose of definition? Not
Yes.
just force or displacement will give you the work. Unless you apply force and unless you do not see displacement of point of application in that direction in which you are applying the force, you cannot talk about the work by that force. So I have taken one point, I have taken two forces, and just to demonstrate the fact that not every force will do the work just because the point of application has moved. Work is only said to be done by the force if the point of application having some component parallel to the force actually. Is this clear what I'm saying?
Yes, sir.
So for example, if I again give you a question, let's say we have a horizontal track. We have a block, and if I do the free body diagram, we have mg, we have normal reaction, and we do have some applied force this way. And imagine the object goes from there to here. So this point has now come here. Let's call S. And if I ask you that in the due process, what is the volume in normal reaction? Tell me, what is the volume in normal reaction?
FS.
How much this force has worked in this process? Okay, how normal will act? Normal act at the bottom, right? Like this.
Yes.
This is the actual normal position. And what is the work done by this force when you go from there to there? Again, go back to definition. What is the definition?
So product of magnitude of force and displacement uh, of the point of application of force in the direction of.
So what is the work done?
So 0.
Very good. Because in the direction of normal, the block has not moved at all. Isn't it?
Yes.
Do you understand or realize?
Yes.
So the whole idea is If you know the definition, then only you can answer. Just multiplying force and displacement is not the work. Work is force into displacement of point of application of force in the direction of force. If you don't see any component in that direction, no work is done. What is the work done by gravity in the same process?
So 0.
And what is the work done by F?
Fs.
Do you realize this?
Yes, sir.
Very good. So we'll just slightly go ahead. And remember, we are doing the constant force. So if I create an inclined plane and let's again draw the ABD, okay? And see how easy is this. Just try to realize. Let's say there is a coefficient of friction also. So it will experience frictional force. And it will also experience the gravitational pull. And imagine this block goes from there to some distance down the plane. Okay, so just so you go from there to there. Okay. So we know from the ABD other things as well. What is the work done by normal? This is friction. And because you're sliding, which friction will be there? Static or kinetic?
Kinetic.
What is the work done by normal?
0.
What is the work done by kinetic friction?
So 0.
Okay, so when you move against the force, the displacement is said to be negative. That's it. So we don't have zero displacement. What we have is negative displacement. Because the line of action of force and the displacements are parallel. It means there is a component, right? So component need not to always in the same side, it can be in the opposite side as well. So whenever we see component to be opposite, what we call,
Negative displacement.
see the point of application is moving, yes or no?
Yes.
Point of application is moving, no? In which
Yes.
direction it is moving?
Opposite direction.
To the force. Correct?
Yes.
So it is opposite to the friction force. Opposite is not zero. Perpendicular is zero. Okay, so how to write the answer? Minus Fk into S. Why minus? Because force and displacement are
Opposite and
opposite.
direct.
So if you go by the vector definition, what is the definition? A B cos theta. Cos pi. Cos pi is how much? Cos pi is -1. Right? Hello, hello, hello.
Yes, sir.
Okay, what is the work done by gravity? So you can always draw a triangle like this. Because I am drawing this because this is the gravity direction. This is theta. This is the displacement. What is the displacement in the direction of force? How much you have moved in this direction? Vertically downward.
0.
Hmm. So when you go from here to here, you go 0 in this direction.
So, root of
You don't
s
understand
square
concept.
plus s
You
square
don't
minus
understand.
mg.
You don't understand component. You've done component in vector, right?
Yes, sir.
What is the component of S? S is the displacement. So what is the component of displacement in the direction of force? Tell me.
S cos theta.
S cos. Are you sure?
No, so in the direction is s sin theta.
So if you understand this simple thing, then you're done. So it is the force into, and you can see that displacement is also downward only, right?
Yes.
This is the answer. So in the ABD, we had 3 forces. So we wrote 3 separate work. And always remember, force may be vector, but work is scalar. So these are values. So how to interpret this? What is the 0 meaning? These all are called work done by the force on the block, right? What are these things? Work done so it is like there are 3 separate buckets. The normal is giving you how much energy? Tell me. Are you receiving something from normal? Is normal reaction imparting or giving or taking something from you or giving something to you?
No, sir.
That's why the 0. What is the work done by friction is negative? What does it mean? A negative means the energy has been taken away from whom?
From the block.
From a block. But a block is like a mass. Mass cannot store energy. You know why block is, I mean, how friction is taking energy from block? Any guess? Because gravity is giving energy now. You can see the next part. How much gravity is giving energy to the block? Tell me. Gravity is doing which work? Positive work or negative work?
Positive.
So positive means you receive, negative means you lose. That's it. And zero means nothing. So how much are you receiving? Tell me.
Mg into S sin theta.
Correct. So what you need to realize that you can write it this further up. So the work done by friction you can also write as minus Fk. Fk is written as mu mg cos theta. Correct? And this is mg sin theta into s. Is this clear?
Yes.
Now you have to actually go to the force definition. Which force is bigger? Mg sin theta is bigger or mu mg cos theta is bigger?
Mg sin theta.
Because it is going down.
Yes.
So the one which is giving you energy is bigger, and the one who is taking energy away from you is smaller. So you are getting some energy, and a part of that energy is snatched away by the friction. But what energy is taking away from you is still less than what you are receiving, yes or no?
Yes.
So what is the total amount of energy left with you? What is the net energy you have available, the block will have?
Mg sin theta into S minus mu mg cos theta.
I can take mg into s common. It is sin theta minus
Mu g cos mu cos theta.
mu cos theta. What is this? This is the net energy available to whom?
So the block.
Now, block is a point mass. Point mass cannot be deformed. So this energy is available to a mass. Then how you're going to show off to the world? See, this is the hidden thing. No one knows that this energy. This is the energy you finally received. But how you're going to show off? How a particular mass will show off its energy? Remember, you can't hide it. A mass cannot hide the energy. Yeah, a spring can hide, but a mass, no, it cannot hide. So how you're going to manifest your energy to the world that you have this much energy? See, I have energy.
So by showing displacement.
No. How you will show to the world? Let's say you buy a earring and you want to show to your friends. What will do? Will you keep in pocket or will you wear in your ear? Of course. What will do?
Bearing.
You will wear it. So in physics, the show off is called kinetic energy. Understood?
Yes.
So kinetic is the show off. So this energy will show off. So simple. So the world will see the kinetic energy. This is the energy you're showing off because you received from someone else. And if you solve, what is V square equals to? You can see M gets cancelled, right? 2GS. Isn't it?
Yes.
And if you that in laws of motion, we know the acceleration of the block will be G times sine theta minus mu cos theta, right? From laws of motion.
Yes.
And therefore, this is basically 2AS. And this is how we used to solve from kinematics. You start with 0, you have acceleration A. Then what is the V? If you travel S, so we write V square equals to U square plus 2AS, right? And U was 0, right? And A you got you can realize both are same answer, isn't it?
Yes.
So in one hand, you have a power of laws of motion and kinematics. On the other hand, you can just write the energy relation. And you can feel that if you really understand the energy relation, it's very organic. You can always solve, isn't it? So we have solved one of the questions without actually understanding much of this chapter. What we need to understand? The idea of energy. And a positive energy means when a positive work is done on you, it means the force has given you energy. And negative means it has taken
Taken away
away the
energy.
energy. So here the positive and negative will have a meaning actually. Okay. Energy is not negative, but plus minus will represent the direction of flow. Understood what I'm saying?
Yes.
So is energy negative?
No.
No. Can you give someone negative water? -1 liter?
No, sir.
No, but you can interpret this. See, minus, I have given you -1 liter, which is like, okay, you have given me 1 liter. Okay. So these are mathematical interpretations, and as a student, we need to understand the meaning of this interpretation. And always remember that there is nothing like potential energy. So when we are solving question of this chapter, never ever think of potential. Okay. I will tell you when is the right time to think of potential. Also, you need to remember that which work is positive, which work is negative, what is the interpretation. And if a mass M is receiving energy by a force, it means the work done by that force is positive, and negative work done by a given force represents that force has taken energy away from you. Does it make some sense to you now?
Yes, sir.
Are you able to realize what is work?
Yes, sir.
So imagine a person is walking, of course, without rubbing the sole of the shoe or slipper on the road. Now let's say you're just walking on the floor inside your house. So when you walk, can you mentally draw the ability of force acting on you? Imagine yourself, imagine the ability also. Do this hardcore visualization. Create your own image in your mind. Okay. So now I think your everybody is ready.
Yes, sir.
Tell me, by thinking very carefully, you think very carefully. You can see the friction force acting on your foot
Yes, sir.
as you walk. Is that friction doing work on you? Yes or no?
No, sir.
Why?
So it is doing negative work.
So negative work is also work only. Is it doing work means either positive or negative? If it is zero, then there's nothing. So as long as it is positive or negative, it is something. So as you walk, then friction will do some work. Positive, negative, zero. Which one?
So negative.
Why you are saying negative? Do you have any realization, or you're just saying because of no reason? Do you see something? The motion, the force, the point of application, the displacement of point of application. Do you see all these things? Then you're saying, or you're just saying,
Yes, sir, because it is in the opposite direction of the point of application of force.
hmm, what is the opposite direction? Okay, go and walk and realize that is friction displacing the point of application.
So friction can be any one of the following.
So when you walk, which friction is acting?
Static.
And wherever it is acting, is it moving that point wherever it is acting?
Yes, sir.
So when you walk forward, then what is the direction of friction acting on you? So when you watch lecture, do you make yourself blindfolded and put the earplug and then watch it? Or do you really listen to things carefully? Because this part we have discussed quite a lot in friction.
So in the forward direction.
And when it is acting, when you touch the surface, when you put your foot in air.
So when we touch the surface.
So imagine a person who is walking. So imagine a person who is walking. So when you try to walk, you press the surface backwards, so you experience the friction forward. And what do you do next? What do you do next?
Lift
You
the
don't do
foot.
that. You simply lift the feet. I mean the foot. Okay. And once you lift it, friction is going to zero, right? There's no friction.
Yes.
And as long as it is touching, is it moving your foot forward or backward or anywhere else? Or is it just holding there?
Holding it.
So is it moving the point of application? Is this point moving anywhere?
No, sir.
So what is the working by friction?
0.
This is the most important concept. Walking or riding bicycle, driving car, riding bikes. So things with tires, wheel, or even walking. As long as the friction is required, involved is Fs, and as long as the surface is fixed, if this surface is fixed, the friction does no work, and that is why friction supports in motion. Friction will help you to move, but it will not give you any energy to walk. And therefore, when you walk, you consume your own internal stored energy, the energy in the body itself. And because of the consumption of that energy, you get tired. If friction will give us energy, we will never get tired. In fact, we can walk the entire world without losing our own energy. So you just need one apple and then you can walk around the world. Or you can run as fast as possible. You become the fastest person. Then there is no need to have the mode of transportation. We can go anywhere without getting tired. You can climb the mountain or go anywhere. The idea is if friction can give energy, life will be really sorted. But friction will never ever give you energy. Understood what I'm saying?
Yes, sir.
Do you realize this?
Yes, sir.
Oh, I think I can't go beyond this point. I can go some more. Okay. So walking, or if you have a wheel which is not rubbing the surface, and if you're accelerating, if friction, see, either friction will act like this or it will not act at all. So whenever there's a friction on a fixed surface, work done is 0. But if you have gone to Mumbai airport, you might have seen travelator. Have you seen travelator? So we have travelator, we have elevator, we have escalator, elevator is also called lift. So how elevator moves? Vertical. How escalator moves? At an angle, because it's a stair actually, right?
Yes.
And how travelator moves?
Horizontally.
So if a person is standing on this travelator, so who is moving you? Let's say friction. And as the travelator will move from here to here, is friction doing work on your foot? Is friction moving the point of application? Yes or no? Tell me. You're simply standing on the travelator. Travelator is going forward. So the point of application is moving forward, yes or no?
Yes, sir.
Not realizing what I'm saying. Are you able to realize what I'm saying? You are
Yes.
simply standing on a surface, but the surface itself is moving. So the point of application is in motion, yes or no?
Yes.
And the direction of friction is forward and you're also moving forward. Then is friction doing work in this case?
Yes.
So imagine if you are on a travelator, then work done by friction. And of course, the travelator must accelerate. If it is moving with constant velocity, friction will not act at all. So it will be zero. Okay, if you're simply standing, so it will act for some time in the very beginning. And once your velocity is same as the velocity of travelator, you just move because of inertia and you don't feel any force. So there is no work. So when you just climb the travelator, you embark on the travelator, the friction will act to impart you velocity for quite a small time, and then you move because of the inertia, which you don't realize. This is too much physics, but too much simple. This is too simple to understand. Sometimes something which is very basic is actually very complex. It happens. So the whole idea is friction will do work only when the surface on which it is acting itself is moving. And this is going to be very common problem when you solve the two block problem, which we have again done in where? In friction chapter, right?
Yes.
And if you remember, which is difficult, much of expectation, and if you apply some force on the upper block, and there's a friction, and imagine it is moving together, this is zero. So what I said is, let's say the friction is zero, I mean between the block M2 and ground, and it's a fixed surface. If you draw the ABD, what will be the direction of friction on M1? Any guess? If they are moving together, then
Towards the right.
okay, anyway, I'm trying too much to teach you guys. I mean, you guys are not at all studying it. I can feel it. So if M1 will, if you apply force on M1, what is the tendency of M1 to move, right or left?
Right.
So friction will act on M1.
Left.
Yeah. So much confusion, right? I mean, it's like, this fool teacher is trying to teach you guys because he just want to teach. And you have no respect for the teaching or knowledge, whatever. Just you teach, I'll forget. Again, you have to remind me. It's your duty to remind me again and again, because we are bound to forget things again and again. And now let's say the block moves. Okay, it goes. So what is the work done by friction force on upper block?
So negative.
Negative. How much? What
Minus
should I write?
Fs into S.
Minus Fs into S, right? And what is the work done by friction on N2?
Fs into S.
So what you realize? What you can infer from this entire discussion? what you would like to say about friction in this particular case? Do you want to say
It
something?
can be negative and positive.
Hmm? Mhm.
Friction can do negative and positive work.
Yeah, friction can do positive work also. Friction can do negative work also. What else? If I take M1, M2 as system, then this friction will become which force? Internal or external?
Internal.
Pardon? So if I ask you, what is the friction work on M1 plus M2, like on system? Then what is the answer?
Zero.
What does it mean? Friction cannot provide energy to system, but it can take energy from one part of system and give it to another part of system. So this friction is taking energy from which block?
Um,
Hmm? This
um,
M this friction is taking energy from which block? M1 or M2? Am I audible?
yes.
So the friction is taking energy from which block?
So M1,
M1. And giving to which block?
M,
M2. So when you take energy from M1, you give it to M2. So M2 will receive energy and it will show you the velocity. And it is able to take from M1 because M1 is getting from somebody else also. So who is giving to M1? Am I audible, guys?
Yes, sir.
So if you take energy from someone, then that someone, M1 must be receiving from somewhere, right? So from where M1 is getting the energy?
So from the force supply.
So F is giving you energy. What is the energy given to M1 by F? Work
F into
done by F on M1 is how much?
F
Fs.
into S.
Very good. See the entire process. It's so beautiful. You receive energy, then someone will snatch away from you, will give it to other. So this is how the energy get transferred, and this friction we call constraint force. If you remember the chapter constraint, so which forces are called constraint force? Friction, static friction, normal and tension. These are called constraint force, right? And the role of constraint force is to transfer energy without diminishing, without wasting it. It simply takes from one and give it to other. And these things we don't realize in our day-to-day life. Let's say if you go in a car starts and then car starts moving. Do you realize that your kinetic energy is keep on growing as the car is speeding up? Do you feel that part? So you are in a car is speeding up. So the kinetic energy of you as a person is increasing, yes or no?
Yes, sir.
Now, if that energy is increasing, from where you are getting that energy? Someone has to do the work to give you that energy. And do you realize from where you get that energy? Who does work on you? To understand this, you have to draw your own ability in the car. Then you can realize it. So mentally close your eyes. Imagine you are sitting on a front seat or maybe back seat. Can you draw the ability mentally?
Yes, sir.
You can see normal by the bottom seat, and you can also see normal by the front, the vertical seat, right? Your back.
Yes, sir.
You also see gravity. And in fact, you can also have a friction between you and the seat. Okay. Then these are four forces acting on you. Okay. Now guess or try to understand which force is giving you energy. For simplicity, you can take all forces either vertical or horizontal. Don't take slant. So which forces of force will give you energy? To you.
So the double exerted by the seat,
The back seat, the bottom seat, like the bottom or the
the
back?
the back seat.
The back seat. Very good. So if the normal by the back seat is giving energy, so the same normal is acting on the back seat backward. If the normal is acting on you forward, then the same normal is acting backward on the seat actually.
Yes,
So it is doing negative work on the seat, correct?
yes.
What you realize is that the same normal extract energy from the seat and give it to you. So the question is from where the seat gets the energy. So the seat is rigidly, kind of latched with nothing involved with the base of the chassis, right? The body of the car. So you firmly fix it, which again provides some force, which you don't see again. And you extract the energy from the chassis, or you can say car. The question is then from where car gets the energy?
So from the fuel.
Exactly. The car gets energy from the fuel itself. So it is the fuel which gives the energy to the car. That is how the entire world is sharing the energy. In nature, you can describe every phenomena just by the proper exchange of energy. And there is nothing which cannot be explained with energy idea. So it is such a powerful method. Okay, you can realize. So I'll give you something very interesting example. Let's say you use your elevator uh, in your flat apartment building, and you go inside the elevator at the ground floor and you press the button to your floor, and the elevator will take you upward. Now, if I ask you which force is the responsible for your motion upward, again you draw your own ability. You're
So
simply
the
standing.
normal
Yeah. So
exerted by
normal
the
is normal working on you? Is the point of application moving upward as you go up? Yes or
yes,
no?
yes,
Because you always keep the contact and the point of application in the ground frame is rising up. So is normal doing positive work or negative work?
positive,
And gravity?
negative.
So to take you to your respective floor, the gravity will snatch energy from you, but that must be replenished or compensated by whom? The normal. So whatever Earth is taking from you is given by the normal to you actually, which you don't realize. So in the due process, do you consume your own internal energy? Do you consume? Yes or no?
Yes, sir.
And because you don't consume energy, so you don't feel tired when you go up the lift. Understood? And if the normal is giving you energy, then normal is taking energy from somewhere. From where? From where the normal gets the energy? Do you realize this? From where you get the energy?
So the force that is pulling us up.
No. You can't go that much beyond. So normal on you is upward, so the same normal will act on the elevator downward. It is always action reaction pair, right?
Yes, sir.
Same normal is doing the negative work on the elevator. Do you realize this?
Yes, sir.
And giving to you. So normal is extracting energy from the elevator and giving to you. But if normal is extracting energy from elevator and gravity is also extracting energy from elevator, then who is providing that energy to the elevator?
Normal.
No. The tension in the cable. Every elevator will have a cable. Do you realize this? Elevator will have a cable. Not just one cable, there are many cables. If you see the so elevator is like attached to a cable. And of course the side support, okay. If you see, it is between the two tracks actually. It's a track in which we have the iron wheel on which you roll actually. It keeps things really simple, smooth. And there is also there's a sufficient space for cable to go down. So cables are not only attached there, cables are also attached here at the bottom. And as you go down, the cable is thrown to the top, and it is attached to something called motor also. So anyway, I'll just keep it simple. And you as a person, so I'll make it simple because this guy is not heavy. So this guy is simply standing on the elevator. And if you draw the ABD, and that's why I say ABD is a very, very essential part of learning physics. For simplicity, I'll draw normal like this. I mean, of course, it's acting on the bottom. MD like this. This is the ABD of man. But if you draw ABD of the elevator, normal is like this. Correct? And tension is like this. And of course, the elevator will also have mass. So as elevator goes up by S, the tension is acting on elevator or man.
Elevator.
So when you go up by, let's say, H, so what is the work done by tension on the elevator? Plus or minus?
Plus.
How much? Assume forces are constant. So work is how much? This point of application will go how much above?
H.
So what is the work done?
T into H.
Simple. But this normal is acting here and it is going upward. So the work done by normal on elevator is how much? Then me, how much?
So it is acting in both the directions.
No, not both. See, elevator will experience downward only. No? The man will experience upward. So man is a different entity. You have to throw out the man to draw the ability of the elevator, isn't it?
Yes, sir.
That's why I say, if you know the ability, a lot of problem will be solved automatically. So when you draw the ability of the elevator itself, you have only force tension. Normal. MG. Where is the man? Man is separate thing. So you draw the ability of the man separately. Don't mix. And then you go S, it is so H, you go H, this is also going H. And then at the work done. So what is the work done in normal elevator?
Minus n into h.
Minus N into H. Okay. And what is work done by gravity on, I will just write G on elevator?
Minus mg into h.
What is the work done by normal on person
N into h.
plus what is the gravity on person?
Minus mg into h.
You know what happens? Of course, you know what happens that the work done by normal on the person is positive because it has to overcome the negative work of gravity. So this energy is compensated by this force because we know that n is equals to mg. If elevator is going with constant speed, let's say the velocity is constant. Because generally elevator accelerate for very small duration, like first fraction of second. So when you press the button, the elevator will accelerate for just fraction of second. And that is sufficient. The rest it will just move with the constant velocity. Again, while stopping, in the last moment you will have a jerk and it will stop. It's like a quick retardation and stop. So what you need to realize, a lot of things you need to realize in the process, that the man, because if you draw the ability of the man, the n equals to mg. Correct?
Yes, sir.
Because there is no acceleration, right? N equals to mg. And you can also write t equals to n plus mg. So if you look at the energy flow, it's very interesting that T is the biggest force, of course. So T will give energy to elevator, out of which N will take away, mg will take away. That's okay. That's right. But the N will again take away the energy from the elevator, but give it to the person. And the energy given to the person will be taken away by the gravity. So at the end, you will have no energy. When you reach your floor, you will have no extra energy. Otherwise, you will jump up, right? But that's not the case. What is interesting to know or note here that there is a continuous energy flow between the person, the floor, the cable. And the cable is actually pulled by or wrapped by some motor system. So the motor is again driven by the electricity. And therefore, to operate the elevator, we need to pay energy bill, right? Because we're consuming the electrical energy at the end of the day, which comes as a maintenance charge in society. So in society, elevator is a common amenities which is used by all the resident. So at the end of the every month, what you pay? A maintenance bill. Do you remember? Have you seen the maintenance bill coming to your home?
Yes, sir.
So what is that maintenance? We pay the energy bill because you consume the energy in the due process of going up, down every day, day in, day out. So the constant operation of the elevator always have this relation, but they design in a way to consume less energy. How they design? So they always hang the, from the bottom of the elevator, the equivalent weight. Okay. So what they do is, as elevator goes up, something comes down. It is like the energy which I need to lift you is actually kind of retrieved by the gravitational potential energy. So we consume less of electricity because we kind of counterbalance the weight of the elevator by some other weight actually. So we have some other weight which counterbalances, and this is how the entire process runs. Okay. So if we have to always pull it up by the tension only, it is going to be slightly expensive job. Okay. So we do need tension to balance the other forces. Some extra force, the person entering the elevator will increase the weight. So we need to just overcome that extra weight. Rest is generally balanced. Okay, to keep it balanced. So that is how the elevator works. And you can also realize the flow of energy in the entire due process. Okay. But anyway, this was just idea to understand that how energy flow in nature. What is the meaning of positive or what is the meaning of negative work? We'll come to this again as a very short problem. But let's go back to the very basic definition of work done, how we write it. So I'll just do this formal writing process. And this chapter is very organic. You just need to realize the ability and realize the energy flow. If you can do it, you will enjoy this chapter. Else, you will not enjoy much. And I will request you to start studying physics. It's not so boring thing. It's a really interesting chapter. You have to solve a lot actually. I mean, you guys are not spending time in solving numerical. You solve 1, 2, or 5 questions and you feel happy about it. So how many questions we need to solve? Maybe 100. Till you realize. I mean, depends on how much you need to realize. So let's say a block goes from this point to this point under the action of a force. The force is acting this way. Always. Let's take this angle as theta. You know, I can draw something like this. I'm drawing a perpendicular to the force direction. This is called line of action of force. And this is your displacement. I can also resolve the force as F cos theta and F sin theta. Okay. So there are two ways to calculate force, calculate work done. Okay. So we have a phrased definition. What is the definition? What is the work done of force? I want to find the work done by only F force, not normal gravity. What is the definition? It is defined as the product of force, of course, the magnitude of force, into displacement of point of application in the direction of force. See, actually, my point of application has gone from here to here. But what is the component of displacement in the direction of force? So you need to realize that to find the component, we always draw perpendicular to the direction in which we want the component, isn't it?
Yes.
So you may make mistake like this. Some people draw like this. No, this is not component. See, if you have any vector and if you want the component in any direction, you draw perpendicular like this. This is the component. Or if we have vector like this, and if you want the component of A on B, so you draw. So the direction in which You want the component you will draw perpendicular in that direction. I hope this makes some sense to you. Do you realize this part? So what
Yes.
is the component of displacement in the direction of force? I mean the point of application. What was the definition? It is defined as the product of force and displacement of point of application in the direction of force. So are you moving in the direction of force? Yes or no?
Yes.
Are you moving in the direction of force? No. You're moving at some angle, right? You're moving this way. Force is this way. So are you moving in the direction of force?
No. But at an angle.
Yeah. So will it have some component in the force? So what is the component of displacement in the direction of force?
S cos theta.
S cos theta. Very good. So what is the definition of work? Force into
S cos theta.
done. It is simply F S cos theta. Over. But we need to also realize that work is a scalar and work done by a force can also be written as work done by its component. The sum of work done by its component. So this is the method 2. So in method 1, what we do is we don't resolve the force, we keep the force the way it is. And we just simply take the component of displacement in the direction of force and we simply multiply it. That's simple answer. Or the other way around is don't disturb the displacement, rather take the component of force and multiply it. You can clearly see which of the component cannot do the work, F sin or F cos.
So can you repeat?
For the given component, which component cannot do work?
So F sin theta.
Because in the direction of F sin theta, we don't have any displacement, right?
Yes, sir.
But in the direction of F cos theta, we do have displacement. So if you treat this as a force, then you can see what is the displacement in this direction of force?
Yes, sir.
Only
F
S,
cos
right?
theta.
It is S.
Yes, sir.
So the answer is eventually same, right? So what you learn from this discussion? How to find the work done? There are two ways. Either don't resolve the force, just see the force the way it is, multiply the component of displacement in that direction, you get the work. Or don't
Take the
disturb the
component of displacement in the
force.
direction.
Take the component of what?
Displacement in the direction of force.
That's the first method. What is the second method? Take the
Take the component of work which is not
component of force in the direction of displacement. That's it.
yeah.
See, that is the basis of dot product. A dot B means what? AB cos theta, which means either A multiplied by B cos theta or so either force into component of displacement or component of force into displacement. Is this clear? So no need to write this. You can simply think that F cos theta into S, F cos theta into S is the answer, or F into S cos theta is the answer. You have to think mentally which one is convenient in which situation. So how to calculate work? Either resolve force in the direction of displacement multiply it, or resolve displacement in the direction of force and multiply it. Do you realize both method? Yes or no?
Yes.
So in vector form, you write work done by constant force as F dot S, which also write as F dot delta R. We have done this in vector, but remember. And now you can write in component form Fx I cap. And dot means what? The component will multiply together. Do you realize this? A given component will only do work when there is a displacement in that direction. Hello, hello, hello.
Yes.
So imagine a block is sliding like this. So what will be the work done by normal?
0.
In gravity.
0.
So the only thing which can work is friction if available, right? So because the friction is acting backward, it will extract energy or give energy.
Extract energy.
So when the block will come to rest? When its energy is 0, right?
Yes.
So let's say in doing so, you have traveled S. So what was the energy available to the block in the very beginning? What is the energy with you? How much you are showing off to the world as of now? What is the energy with the block in the very beginning? How you show off the energy? Kinetic energy, right?
Yes.
You show off kinetic energy. So what is the energy available to you right now?
Half into m into v naught square.
And when you travel S distance, how much energy the friction will extract away from you?
Minus fk into s.
So can I write mu mg into S?
Into s. Yeah.
And when you come to rest, it means what is the energy available now?
0.
So simple, no? So we can see S is how much? I can find how much you traveled before you come to rest. Hello, hello, hello. Is this clear?
Yes. Sir.
If you want to solve by the laws of motion, it's easy. We know what is the retardation because velocity is right, force is left. What is the retardation? Fk by m, which is mu g, right? And then we can write as v square equals to u square plus 2s. So v is 0. What is u here? And A is minus here, it's a retardation, so A is minus 2 mu G, and then you can say is question. So you're using kinematic equation to get the answer, but here you're using the energy relation. Which one is more organic, like easy to understand, right?
Energy.
So if you can learn energy, you can master a lot of physics. It's clear?
Yes.
Okay. If I just change this same problem slightly like this. And see, this question we have done in friction, but now we'll do with energy idea. So we have a tiny block. And if you remember, the half path is rough and half is smooth. So bottom half is rough and the upper half is smooth. So this is mu 0, but here we have mu. Okay, but unknown. But there's some mu, but this is unknown. You start from rest and you come to rest here. Ignore the dimension of the block. Can you find a mu? So if you go from top to bottom, who will give you energy continuously? Which force?
Gravity.
Yeah, so which component? Gravity as a whole or gravity component? Which component is in the direction of displacement? What is the
G sin
component of
theta.
gravity? Yeah, so the gravity will have the mg sin theta in the direction of displacement, right?
Hmm.
And how much you travel?
Yes.
How much you travel? From top to bottom, how much you travel? Tell me.
2L.
So this is the energy you receive by the gravity, right?
Yes.
And how much friction will take away energy? Minus mu mg cos theta into how much? 2L or L?
L.
Only L. And now how much energy you have? You start with zero energy. You get this much, you lost this much. And what is the energy left to show you? Show off.
0.
And if you solve this equation, what will get mu equals to 2 times theta. See, the same question we did with so much effort. Now this is solved in one line. Oh, do you realize this? How we solve?
Yes.
Pakka.
Yes. Sir.
Great. So we can do a lot of questions just by common sense. And always remember what you show off is called kinetic energy. So you start with some energy, you may start with zero energy, you receive, you lose, and whatever is left is the energy. If you know what is left, you write the value. If you don't know, you write variable, half mv square. Okay. So so this is again a common question. So this is the entire plane is rough. And we have block. And you give energy V naught. So what will happen as it will go up? What will happen? It will lose energy. Why? Because gravity will take away as well as what? Friction, isn't it?
Yes.
So eventually it will come to rest somewhere. And then again it will start going down, isn't it?
Yes.
Assume the mu is less than 10 theta, so it is more than repose. I mean, repose angle. So it will again start going down. So in the return journey, what will be its velocity at the bottom again? In the return journey, find a speed of block at the bottom again. Don't try to solve by kinematics, try to solve by energy. Like you first try to go for the upward journey and then write for the downward journey and you will get the answer. So do it and see for yourself. Try to write organically, like whatever is happening, try to express.
So from the first equation, we find the distance it traveled.
Correct, correct, correct. And then use that distance again to write the downward journey to get the speed.
Okay.
Now, with more experience, you can do it even faster, but right now you could do it. So let's say you reach the topmost point after traveling L distance. So how to start with? You write half mv naught square, the energy which you start with. And in the due process of going up, you lose energy. How much you lose energy?
Minus mg sin theta into f. I mean L.
Minus, minus
Mu
mu mg,
mg cos theta into L.
and you then come to this. Okay, this is question 1.
0.
So when you come back, the gravity will give you energy. How much? So for the upward journey, for the downward journey, what is how to write equation? You start with no energy, right? You have zero energy, and then you receive mg sin theta into L, and then what next? Tell me what next? Then friction will again take away, right?
Minus mu mg theta into
But what you are getting is more than what you're losing. So this will be equals to the final velocity v. Let's call v. So in the return journey, you can assume the speed as v, and then you can solve by assuming the energy as speed as half mv square. And so to get the answer, you have to just find L from the top equation. So you can get L from the top equation. Huh? So I can take
So I
mg.
got it as V naught square by 2g into sine theta minus mu cos theta.
Yeah. So I'll just do this. So V square is 2GL minus mu cos theta. This is all 2 implies. And what 1 implies? So 1 implies V naught square equals to 2GL.
Into sine theta minus mu cos.
And then what you can do is you can divide the two equations. That's easy, right? Because G2GL gets cancelled. Isn't it? And this gives the V equals to V naught another.
So it should be sine theta minus mu cos theta.
Just a moment. Just tell me.
In the first equation, it should be sine theta minus mu cos theta.
In the first, here you're saying here.
Yes.
Why? Both are 2 plus. No? Half this equals to this to go that side. So open plus, right? Both are negative. No? So when you go up, both will take energy away from you, right?
Yes, sir.
So at the topmost point, you come to rest. Okay. And this is the equation. So if you solve this question, what you get? 1 implies this much, no?
Yes, sir.
And 2 implies this much. Correct. And then we divide. So we have the answer sin theta minus mu cos theta upon sin theta plus mu cos theta. We can solve many kind of calculative question, many more cumbersome question with a less writing if you know the energy way of writing. Okay. And what we need to understand is one simple thing, that how to write. That's it. You just need to know how to write it. So what you're doing right now is called the work energy theorem in this chapter in physics. But even if someone is not knowing the name, something called work energy theorem, you still can make it without much difficulty. So this is very organic chapter. I won't say when I studied this chapter for the first time, I didn't understand what is work energy theorem at all. And I realized that I remember that day I was able to solve the entire theorem with ease with the common idea of energy flow. That's it. So I was doing every question organically and then realized that okay, this is a much faster way. You need not to study anything in physics. You apply the common sense. Energy is coming, energy is going, energy is left. And the moment you develop this intuition about energy, you become really powerful in solving numericals. So you're not depending on any formula, any category of question. You just apply your common sense, like how to write energy relation, how I'm receiving, what I'm receiving, what I'm losing. It's like complete banyagiri. Okay, so if you know, it's like you lose, you gain, and you're done. You think in terms of profit, loss, and you're done. Okay, so this is organic chapter. I won't say try to force yourself to study. Try to realize the energy flow, energy relation. Try to write the things in that way, and you will find yourself in a very comfortable position than before. Okay, so what you can do as a homework is I'll just give you homework. it is easy. I mean, this chapter is actually easy, but it will take some time. So try to solve the first maybe 15, 16 question. Okay. So you keep on solving as much as you realize with this knowledge, whatever you can do, try to do it. The rest I will do in the next lecture. Okay. So we haven't started the chapter. This is just like the preface of chapter, but that is sufficient to solve SC Verma kind of question. So you can solve entire SC Verma with this simple knowledge. Okay. So you need to know something called spring force, another force, then how they work. So that is what we will do in the next lecture. We'll try to finish as soon as possible, maybe in 4 lectures. And this is pretty easy chapter. Okay, you just need to know certain things about properties. You need to know certain tricky question, how we solve, trick questions. Some properties you need to remember as a fact. Then only you can do it. Okay. So I'll stop the lecture here and see you in the next lecture. Homework is SCV 1 to 50. Okay. That's you can start with just to your own realization. Try to do it organically. Don't try to go into formula and all. Just feel it and you're done. Bye and take care. And